So I'm dedicating this lecture this morning to four people. George, you can guess his last name, and Ada Lovelace. Her 200th birthday is coming up on December 10th. And then Lewis Carroll, really that's not his real name, and Alice Liddell, who is and Alice in Wonderland was published 150 years ago. So this is kind of a tribute to logic and nonsense. So you all have a copy of the handout, which is a take-home exam. Now this explain the handout a little bit. This is an excerpt from something that's on the web that I haven't made clickable yet. But the URL, if you look at the back page where it says Answers to Exercises Abbreviated, a little before the middle of the page that says see HTTP such and such and such and such. Okay, so there's a whole page of stuff missing that I didn't put on this page at that URL. And that URL is probably going to go live in a month or so. But right now, this is the first draft of the section of Art of Computer Programming that's going to be Introduction to Backtrack Programming. The idea, really fundamental idea of backtracking. And then this comes from the exercises at the end of that section, because it turned out that this particular questionnaire is a terrific example of how to write a backtrack program for a medium complicated case. So anybody in the audience ever heard of backtracking before? A few are nodding, but nobody's raising their head. Who has not heard of backtrack method? Okay, well, okay. So the idea of backtracking is so simple that you probably have heard about it. You just didn't know it was called that by some people. So it just says that you have to go through a zillion possibilities, and you go systematically and you try something, and then if that doesn't work out, or after you've explored all cases where x1 equals 1, say, then you backtrack, and so whenever you get stuck, you go back and reconsider the previous decision you made, and eventually you've tried everything. But the advantage of it is that you don't have to try all the cases, because a lot of times you can cut off early and say, well, I know that already I've made 4 choices, but I'm never going to complete the other. In this case, there would be there's 20 questions. You'd have to answer 20 questions. So we save a lot of time, and furthermore, it's extremely easy to handle in the computer because it doesn't need much memory at all. You don't have to remember a few of the decisions you made in the past, and then you don't have to remember everything you've done. So you're going to go through a huge number of possibilities, but only with a little bit of overhead. Now, so let's take a look at these 20 questions. I guess I should introduce the thing. There's a guy named Don Woods who was a Stanford student in the 70s, and he's famous for 2 things, maybe 3 now with this. And the first thing is a game called Adventure, which was the first cave exploration game, which actually led to the gaming industry in a way, and it went exponential in the 70s, so that people had to limit the number of hours per day the computers could be used to play Adventure. So it's I don't know if any, it still exists on Unix systems. You can ask for Advent, and it features things like being lost in a maze of twisty little passages all alike. Does anybody know this game at all? You do? Yeah. Okay. So anyway, Don came up with that, and it went. It just took off, and it led to all kind of computer games. Then he also was co-author of something called Intercal, which I doubt if anybody knew. But anyway, this is the world's worst programming language. It's so difficult to even to add two numbers together in Intercal that you feel really proud of yourself if you've gotten through. Hey, there's great seats in the front row. Come on up here. So now this 20 questions is something that he posted on the internet about 2000. And it's based on another thing that was circulating called the self-referential aptitude test by Jim Propp of the University of Wisconsin. But as usual, Don took an idea and made it into something that was really, I said in the abstract, I said insanely great. So it has sort of everything that can go wrong with a multiple choice exam is here, but it also makes a great exercise for how to write a backtrack program after you've mastered the fundamental techniques on easier cases, and I think this makes a good one. That's why I put it in my book. So the question is, find all ways to get the maximum score on this questionnaire. And so all you have to do is, for each of the 20 questions, you have to say A, B, C, D, or E, and then that's it. Now, the scoring is the number of questions you get right. That seems fairly simple until you start looking at the exam and working out. So anyway, you see the first question whose answer A is A1, B2, C3, and so on. So if I answer A to question 1, well, that looks okay because the first. But if I answer B to question 1, then I have to answer A to question 2. You with me on that? Okay. Now. And so we go on, and we get to. We'll take a look at number 6. So what's your answer to question 6? Does anybody have? I'll tell you if it's okay or not. Anybody in the front row? Can you answer? Too hard? Flip a coin. Well, okay. Okay. So you can't get question 6 wrong. But on the other hand, there are some of these questions will say that you can't have any two consecutive questions with identical answers. So look at number 3, you see. And so if you change your answer to question 6, that might make it identical to the answer to question 5 or to question 7. And so even a question like this that looks like you can't get it wrong, you can get it wrong because if you don't answer the right answer to 6, then you might screw up on some other question. Okay, so this is I guess you might say this questionnaire is a professor's dream, but then you start looking at the problem of programming it, and the interesting thing is that after it was posted, several things happened. First of all, there were lots of nonsense solutions published, but the main problem was that there were also some solutions published that the phrase is that they cooked Don's problem. Don had written a computer program where he thought he had answered his questionnaire in the best way, but he had bugs in his program, And so, in fact, there were lots of solutions to the thing that he had, maybe dozens and dozens of solutions that he hadn't intended at all. And so he considered that his problem had been cooked, and that's because of the difficulty of writing computer programs. I've almost never seen a computer program that of any reasonable size whatsoever that if I didn't work hard enough at it, I couldn't find a bug in it somewhere. Even my own programs have bugs in it. Would you believe? And I paid out many dollars for the bugs in tech and so on. Now, his problem was cooked, and so he came up the next year with a revision to the problem that was supposed to correct those errors, and lo and behold, somebody cooked that one too, and there was another bug in his C code, and on the other hand, there were people tried various approaches to it, not only backtracking, but they tried various other methodologies of random searching and downhill methods and things like this, trying to find the best solution to his answer. Well, when I saw this, I said, "Wow, this is going to be a great exercise for art of computer programming because people aren't getting it right, so they have to be good programmers. They have to learn something about programming in order to do this well. And also, you need backtracking if you're going to really be sure you have the best answer." So I wrote to Don and I said, "Okay, I'd like to include it in my book, but I want to have a new version so that it's not cooked." So this represents what I believe is a questionnaire that I know everything about the best answers to, and that I have a computer program that it doesn't have bugs in it that solves it. Now this computer program, however, has not been proved correct, but it also, the results also agree with one that he wrote independently without looking at this. This program is called Back20Q, and it's on the web if anybody wants to look at it and find a bug in it. So you can go to my website or Google this, and Back20Q will get you to this program. And if there is a bug in this program, well, then this whole exercise goes away, and I have to patch it and do something about it. And of course, I pay you $2.56 because everybody finds an error in my books. That's the reward. But I hope, I hope nobody finds a bug. But I think this program is written in C-Web, which is the language that for literate programming. The idea is that the program is meant to be read, not just to be executed. And so that if you look at it, it explains what's going on and sort of convinces you that the program is correct. I think literate programming is the greatest thing since sliced bread was invented. And I've had wonderful bread here in Ireland this week, but literate programming is even better. So I think the fact that it was written in this way also gives me more confidence that this program is correct. Now, when you get into writing a program like this, pretty soon you find yourself wondering, what does it really mean to get the best score on this exam? So as I started this project, I thought I understood logic. I've been working with logic for more than 50 years, and I thought it was all pretty straightforward, and so I could. But then when the problem with logic has always been self-reference. When things are talking about themselves, then we get to things that are hard to understand, like the set of all programs that don't terminate, or something like that, that led to the Turing's work on unsolvable problems. And we have all kinds of paradoxes based on self-reference, or referring to the set of all books that don't mention themselves, or something like this, and you find some problem with it. So here we have to confront what does it mean. And so on the first page, in the statement of the exercise at the bottom, it has a little sample warm-up problem, which has only 2 questions and only 2 possibilities for each question, A or B. And so we have to understand, what does it mean to have a maximum score on an exam like this, and after sort of tossing and turning, and after a couple of days of finding bad solutions, I finally realized what the correct semantic model is for this problem. And so in the answer, then I give a description which I think clarifies everything, and so we have 2 operations. The problem now involves 2 things. One of them is a student, and one of them is a grader. So a student fills out the exam, and the student comes up with a list, alpha, which is A1 up to A, and there are n questions on the exam. And each of these A's is an element of some set, which is, in the case of the 20 questions exam, set is A, B, C, D, E. And in this simple exam, the set is only A and B. All right? So now so that's what the student does. The grader supplies a Boolean vector, and I could call it B1 through Bn, but I'm going to use X1 through Xn, just because in my book I always use, when I'm solving Boolean equations, I usually use X for the variables, as Boole did actually. So Xj is either 0 or 1. And so then the question is, given a alpha and a beta, a combination of a filled out exam and a grader report, we have to decide whether or not that has been graded in a valid way. So we say that alpha and beta are valid if there's a Boolean if the following Boolean function is true. And now this Boolean function is written on your second page there. Excuse me, I'm coughing, but I'm not really sick. I've just got something in my throat. Okay, so here we have and for j equal 1 to n, and for all s in little s. And then the following thing occurs. If aj is equal to little s, then the variable xj is the same thing as little f sub js of alpha and beta, and these for every combination of a question and an answer, I have a Boolean function, which I'm going to explain in a minute by giving examples, which represents that part of the exam. So this formula is a whole bunch of things, and. So these are actually all have to be true, and so each of these things has to hold. If they all, if each of these things is true, then the alpha and beta are valid. That means the grader has done his job, and the score, the score of the exam, if it's valid, is the sum of the x's. We use 1 for true and 0 for false. So each x is 1 if the grader says you got it right, and a 0 if you didn't. And so the sum of the x's is your score, and the maximum score is you get the maximum score if you've supplied alpha so that this number comes up to be as big as it can be. Now, what do I mean by this funny notation with the brackets here? In my book, I always put brackets around something if I want to convert it to a 0-1 statement. So if it's true, then this becomes 1, and if it's false, it's 0. So now I'll give some examples to make this crystal clear. But if you have some basic question now, before I go into the example, I think the example will actually answer all the basic questions. So let's take a look at the this warm-up problem. So you see, 1A says answer 2 is B. Now, so I've got to have a formula f sub 1A of alpha and beta, and f sub 1B, and I've got to have a formula f2A and f2B. For every part of the exam, I'm going to explain in Boolean algebra what it means. In English, it said answer 2 is B, but the Boolean formula is going to put that into a formal system that is airtight in logic. So, for example, answer 2 is B is the statement that A2 equals B. Okay, so these formulas, these are Boolean formulas, and they involve the variables of alpha and beta. So A2 is a variable that says that if the student, if the exam has B for the second answer, then that's the meaning of this saying answer 2 is B. So now F1B says answer 1 is A. Any guesses as to what this formula is? I'm not going to mark you down if you don't get it, but the experiences with MOOCs say that we should be interactive and we should try you out, and then I give you a green check mark if you get the answer. So somebody call out an answer, and I'll either give you a green check mark or I'll give you a red X.
A1 equals A.
A1 equals A. Okay, now for this we turn to the back of the page. You're not supposed to have done that, right? And it says, look at that, A1 equals A. All right. Now, and if the book had it wrong, of course, then you would have won 56 cents. Okay, now 2A, F2A says answer 1 is correct. What does it mean, answer 1 is correct? No. See, this is the interesting thing. The functions involve the A's and the X's both. And so a statement about what the student did talks about the A's. A statement about what the grader did it talks about B's. But I admit that there's an ambiguity in English, but what I mean is correct. It means that the graders thought it was correct. Because the grader is the one who's doing this. Okay, so what is F2A? Excuse me? Yeah. Yeah, no, yeah. Okay, so that's not what I had in mind when I said it's correct. A statement about correctness is a statement about what the grader thinks is correct, not a statement about logic or I mean, maybe what you said it can be proved too, but there's a much simpler direct result. X1, yeah. X1 equals 1, or just X1. So this, X1 is the statement that answer 1 is correct. Okay, that's what that. Okay, now we get to the complicated one, or the most interesting one, is 2B. Either answer 2 is wrong, or answer 1 is A, but not both. So this is the famous exclusive OR that Boole loved. He didn't like the unexclusive OR. And we had it on our menu last night when we celebrated his 200th birthday. We had our choice of two different appetizers, and it was an exclusive OR. We couldn't have both. Okay, so now, so either answer 2 is wrong, or answer 1 is A, but not both. Okay, so now let's have some suggestions for this. So answer 2 is wrong means what? X2 bar, yeah. So the notation is X2 bar. It means not X2. And then exclusive OR notation is circle plus O plus notation for XOR. And now answer 1 is A, but not both. So A1 equals A, right. So A1 equals A. So this I believe is a rendering, okay? Are you with me on this? So now this is logic and this was English, but we've converted the English into logic. Now we have to say what are the possible results of the different answers to this question. All right, now let's see if there's also an eraser up here. Okay. What? Oh, yeah. Hey. Is this the color of cork okay. So it's okay. Okay. Let's see. Is there a moisturizer? Maybe I'll use some Irish spring water.
You can use the black side.
I can use what?
The black side of the eraser.
Oh, the black side is, oh, that's the eraser side. Okay. Okay. Hey. Okay. Okay, so we have so the student can come up with 4 ways of answering that exam: A, B, B, A, B, B. So these are the possible values of A1, A2 in that little warm-up exam, and then we have this big monster formula here, which has 4 parts to it, 1 for each question. So F, in this case, F of A1, A2 is equal to, well, there's 2 clauses. Since A1 is equal to A, I only have to use F1A and F2A. Sorry, F1A is the one I use here. So I have to put F1A. Okay, so I'll use red to show you what I'm doing here. F1A is going to go here, and this will be F2A. Sorry, F2A here. This is going to be F1A and F2B. This is going to be F1B, F2A. This is going to be F1B and F2B. So I have to plug in to those formulas on that case. So here I'm going to have F. This is going to say X1 is equivalent to something, and X2 is equivalent to something. And this will also the same way. I don't know how much room I'm going to need, but I'm just filling this out to sort of automate what I can do without thinking here. One of the principal goals of Boole's work was that you don't get confused if you can reduce it to a problem about symbols that you can do mechanically and can think about the symbols as the reality instead of worrying about what the symbols mean, and work in the symbol-only world. So now I plug in here F1A of alpha and beta, and so I get here, well, F1A was this statement A2 equals B. So I plug in for A2, and A2 is A, so this is B. Oh, sorry, this is A equals B. A2, yeah, A2 is A. So this is A equals B. And F1A was, in this case, B equals B. So that's F1A, where I substituted in the value. Now, F1B is A1 equals A. So that's 1 equals A, and F1B, that's the wrong place I put it. F1B it goes here. So this is what is it? A1 equals A. I got to put A1 in here. Equals A. And here is A1 equals A, I think. Is this right? Yeah, okay. Now, F2A, I get to stick in here and here, and that is just X1. So that's X1. And F2B is this XOR guy, which is X2 bar XOR something. So I put in here X2 bar XOR something. Okay. And now the something was A1 equals A. So A1 equals A. A1 is this guy. And A1 equals A. A1 is B here. Okay, so I hope I got this right, but this is the test whether or not exams are properly graded. So let's go through and see what that means. Then the first case is the student submits an exam to you. It's got AA on it. You're the grader. What do you say? Well, you first see that X1 is false. He's got it wrong. And X2 is equal to X1, so that one's wrong too. So the score is 0-0. Too bad for that student, right? No points. AB, the answer said, the first one, B equals B. That's good. So we got a 1 there. And the second one says, exclusive OR of X2 bar and A equals A. This is always true. And if you exclusive OR with x2 bar, you get x2 again. So this one turns out to be it works in both cases. So we learned this about Boolean algebra, that x2 bar is equal to x2 XOR 1. And so adding 1 is like complementing in Boolean algebra. And so this complements twice, and x2 is equal to x2. So it works. So the grader it is okay grading problem 2, either saying yes or no. Both of them are legitimate, valid grades. With me on that? I mean, that's the point of Boolean algebra is that you can't argue about it. The symbols tell you what's going on. Now, B equals A is false. So this exam BA, it's got to be 0 here. And this one, x2 is x1. So again, this student who fills out that little exam and says BA has lost. Both of them. What's this one? This one starts out with a 1. x1 is false. And then x2 here is x2 bar or 0. But this says x2 is equivalent to x2 bar. That is impossible. So there's no way to grade this exam and be valid. No matter which way you try to grade it, it contradicts this formula. And so you got to throw this exam out. It's not correct, it's not false, it's not gradable. There's no way to grade it. So here we have a case where there's 2 ways to grade this exam, and 1 way to grade these 2, and no ways to grade this one. So what's the maximum score possible on this exam? Maximum score is 2, but you're not guaranteed to get it. It depends on the whim of the grader. If the grader's in a bad mood, in order to get the maximum score, you A, B, and you have to have the grader agree that you got them both right. But that's the setup in which self-referential problems have to be understood. Some questions on this? Okay, so we're working on it. So now we've got 20 questions, and 5 possibilities for each question. So the number of possible exams, the possible ways to fill out this questionnaire is 5 to the 20th. It's a bigger number than you want to actually compute, even on even with multi-cores and a cluster and so on. It'll take a while, but that's not all, because there are 2 to the 20th ways to grade it. And so the number of possible combinations of exams and grading is 10 to the 20th, which is easy to express in decimal. It's 1 and followed by 20 zeros. And that is bad news, because 10 to the 18th is about as far as I go. And if I have if I'm the National Security Agency, maybe 10 to the 19th, maybe 10 to the 20th. But design a new FPGA chip or something. But anyway, there's lots of. But on the other hand, it's finite. So every possible combination of grade and grader choices and exam, we can rate it and say whether or not it's valid. And so it seems to make sense. What is the maximum score? We just look at all these 10 to the 20th combinations, and for all the ones that are valid, we compute the sum of the x's and find out which is the largest. Okay. So that's the setup of this 20 questions problem. And now it comes to saying, well, that's lots of cases, but can we use backtracking to solve the thing and find out what's the best answer? What's the best answer? All right. So Well, it's very nice if you can get a perfect score. So the first thing you naturally try is to say, well, just suppose that we set all the x's to 1, and we say that you got to get them all right. So is there? Then we have to run through 5 to the 20th possibilities and say, for each of these, would it be correct if the grader said they were all good? And that's nice. And 5 to the 20th, you could do exhaustively in a few years, but with backtracking, you can reduce it to something like let's see, I think I said here on the back on the back page, where does it say? Well, anyway, in the real book, when you got all the extra handouts, it says, here's what happened. First of all, when I wrote the Backtrack program, I didn't just answer first question 1 and then question 2 and question 3 or something. It was much smarter to start out with question 3, for example, and then consider question 15, and I choose an order so that a lot of the cases will be ruled out fairly quickly. So if I start out with question 3 says, it talks about the only 2 consecutive questions with identical answers are such and such. So as soon as I assume that question 3 is answered by A, then I know that 15 and 16 have to have the same answer, whatever it's going to be, and all the other consecutive questions are all going to have different answers. And so instead of having 5 possibilities, I'm cutting down to, in many cases, only 4, most cases only 4, and sometimes only 3. And so that 5 to the 20th already went quite a bit down. Then I look at answer 15 next, and it says the set of odd-numbered questions with answer A is such and such. So if I say that 15 is answered by A, that means that I know that that answer 7 is equal to A, answer 1, 3, 5, 9, and so on is not equal to A. So I've cut 5 down to 4 in those cases. So it turned out by this strategy, I got down to checking only 52,000, let's say 53,000 possibilities instead of 5 to the 20th. And it took a total number of memory accesses. My program Back20Q doesn't only, all the programs in my book are measured not in terms of the number of seconds it took to get them done, but in terms of how many memory accesses did the program make. Because computers keep changing in speed every year, and when you read a paper from 10 years ago and they said that this took 30 seconds on a certain Pentium or something like this, it doesn't mean anything anymore. But on the other hand, if you know that it made that many memory accesses 10 years ago, it'll still make that many memory accesses now. And so you get some idea. And so everything in my book is always described in terms of MEMS, which means an access to 64-bit word and memory. So this was 3.4 million MEMS to show that it's no way to get a perfect score in this exam. Okay, so, well, too bad but for that, but then, well, perfect score is 20. Let's try for 19. Now here I got to mention problem 20, which is the real killer on this exam. So take a look at problem 20. This is the climax problem, actually, of the whole exam, and which is what had me at various times in stitches and in various times in tears. Because I didn't know what it meant. Okay, but anyway, the maximum score that can be achieved on this test is A, 18, B, 19, C, 20, D, indeterminate, and E is achievable by only by getting this question wrong. Now that's the one that put me in tears. But anyway, it seems that when you think about it, it seems that can't be right. But anyway, here we are. So now I have, by my exhaustive backtrack test, it showed that A is false. The maximum score that can be achieved on this, C is false. The maximum score is not 20. We can't get them all right. All right, so well, let's try for 19. Now, so I set up my program. Instead of trying all the cases where I get a perfect score, I just have to run 20 different cases where I got everything right except problem J. You know, so the grader will say false for problem J, but it'll give me a okay on all the other 19 questions. And so then I can run my program again and see. And it turned out that in that case, a lot of the cases for all J, J equal 1, J equal 2, up to J equal 18, they were all really easy to rule out and say that there's no way to just get that one wrong. It was let me see what were the statistics here. It said only if J equals 15. That was the hardest one of those 18 tests, and I needed only 56 possibilities. I only had to consider 56 branches of the tree in order to rule that. But then I got 3 solutions to the question of getting 19 right, and one of them was when I said had everything right except question 19, and the other 2 were everything right except question 20, and those only took like 10 megamems each to resolve, and so I have those answers on the back of your handout. So there's there are answers 1, 2, and 3. There to the 20 questions that are almost right, and I'll copy just the. It starts out with D, A, D here. This is question 1 and so on. Question 20, I have here capital B, and then I have lowercase c, lowercase e, and here I have lowercase b, A, E, and this was AAB. Now, the convention is I use a lowercase letter if the grader marked it false, and an uppercase letter if the grader marked it true. And so these are valid gradings. You can check it out. For example, question 19 says, the last question whose answer is B is. And so here, if I say the last question whose answer is B is number 15, that's wrong, because the last question whose answer is B is not number 15, it's number 20. But here, the last question whose answer is B is, let's see, that's 14, and it turned out in problem 2, 14 was the last question whose answer is B, and this one, it was 18 was the last one whose answer is B. Okay, so that's the that sort of solves the problem. Then it says we can get 19 points, and in fact we kind of needed all 3 of these solutions too, because if you look at this one, the third solution says answering 20E was wrong. Remember, 20E says you can get the maximum score only by getting this question wrong. And that is false, because there is a way to get the maximum score by and getting this one gets the maximum score and has answer 20 correct. And so that this solution proves that this one is that this answer is false. Okay, and then the other two show that, in fact, you can achieve a score of 19. So this is the solution to the question of the 20-question exam. Now, questions on this? Yeah, in the back.
How did you design the questionnaire like that?
What?
How you designed the questions?
How did I design the questions?
Design, was it?
How,
Obviously, it's
how did Don Woods do this?
if you wanted to come up with unrelated.
Oh, I'm sorry, I have a hearing aid, but it's not working well enough.
How do you design a questionnaire like that?
How do you design a questionnaire like that? Well, so I have never understood the way Don Woods' mind worked. But he did, he sort of, what I think he does is he gets in a box and thinks outside of that box, and then he gets out of that one too, and thinks outside of that one. But he did sort of say, well, what was the worst thing that I could ask, and then he said, well, okay, but make it worse yet. But that's my best guess. But no, he is just one of the people that I think, like Lewis Carroll, had a gift for the right kind of nonsense. Okay, but you can try making up your own, and I have a few more samples on the back of short exams that will be head scratchers. But this particular one, as we'll see, has much more hidden thing. Now, but of course, I should mention that this is only academic. Of course, it's not going to affect Irish economy or anybody's economy. You know, and the fact is, if you change the exam just a little bit, change almost any of these slightly, then it turns out the whole thing is thrown out, and a whole new kind of solutions come in, and that's why his original problems were cooked, because you can't intuit this kind of thing, and so really it doesn't correspond to the real world either, the way laws of physics work. The laws of logic are not at all robust in the way that we're used to in physics. There's not, Brian?
But there is an interesting problem here, which is how do you design SAT problems
Yeah.
that have unique solutions?
Yes. So to get unique solutions, it's like like design a problem like Sudoku that has only one solution, something like that. And what seems to what we really do is we write a computer program and we hope that we only get one, and then we fiddle with the problem and until again it comes out one. You don't intuit it. You can't do it in your head. You just but when there's that many possibilities, there are usually some strange ones out there that just happen by coincidence. There's only one way.
You could imagine a model that searches over clues. So take the Sudoku question.
Yes, you can.
So you search over the clues.
Yeah. So.
You channel into a model that.
Right. So Don found out, for example, that some of these questions didn't filter out many other ones after all. It was very surprising, but only because of the structure of the other ones, the way they hung together. So yeah, but combinatorial problems are very unintuitive sometimes, and that's why we really have to rely on computers and on the proofs of correctness of computer programs. So here, anyway, as I was working on this, I made one twiddle to the problem because I was trying to fix up his quick problem, and I came up with a version that's almost the same as this table 666, but led to a paradox, and that was the title of my lecture. So let's look at exercise 91, which is at the bottom of the first page. And so now I'm going to change the table only in two little ways. And so in answer 9E, Okay, question 9 says, sum of all question numbers whose answers are correct and the same as this one is, and originally it says somewhere between 44 and 53, but now we're saying it's somewhere between 39 and 43. And then in exercise 15C, I'm changing from not the set 11 to the set 11. So we make those two changes and rerun the whole thing. Once again, with those two changes, we find there's no way to get a perfect score. But there's a killer observation, and that is that those two changes also throw out answers 1 and 2. So answers 1 and 2 satisfy the original problem, but they're not valid grades of the new problem. Now we're in trouble because answer 3 says the only way to get a perfect score on this exam is to get question 20 wrong. Now, this is the only way to get 19 on the exam. There's no other way to get 19 on this exam. So the maximum score will have to be 19. However, we got the maximum score by getting 20 wrong. Therefore, this answer is not incorrect, it's correct. And so then we would have gotten 20 points, but that's not right. All right. So it can't be correct that the only way to get 19 is by getting 20 wrong because in this one example, 20 is not wrong. All right. So the conclusion is, therefore, that the maximum score is not 19. If it was 19, this would be a valid grade, but it's not. I'm getting some questions now. Yeah.
So maybe you said this, but you try to maximize the number of correct answers.
Yes, that's what we usually do. Yeah.
Is the examiner treated as an adversary?
The adversary.
Is the examiner trying to minimize your score? You try to maximize the worst case.
Try to get the worst possible score is a good question. I haven't. It's worth looking at. You could use my program back 20Q to answer that. I mean, the minimum score is certainly at least 1 because question 6 you have to get right.
Oh no, but if the student is trying to maximize his score, is the examiner trying to minimize it?
If the examiner tries to minimize the score, I see. You're saying that that something is valid, and you're redefining the maximum score to be the minimum over the over valid gradings. Yeah. Okay. Still, it doesn't change this particular problem, but it could change other. It would change other problems. But in this case, in order to be valid, the grader has to. I mean, these are the only valid. The only alpha and beta which give the sum of the x's equal 19, and the maximum score cannot be 19. Is the first argument. Okay, so now. If the maximum score is not 19, then we have to throw this guy out, and we have to say, well, how could you achieve 18? So now on your handout, I've shown a whole bunch of ways to get 18. It's not exhaustive, but it includes quite a few. So if you look at the middle of the page there, it has solutions 4, 5, and 6, which achieve 18. Like, for example, in question 4, we have answer 3 and 20 are wrong, and in 6 we have 2 and 8 are wrong, but you know the other 18 are all correct. So those are examples of achieving score 18. The problem is that that doesn't work either. Okay, so 4 and 5, those are the only possibilities that says 20C is false. You see problem 4 and 5, the answer for exercise, the answer for question 20 was C, which says that the maximum score is 20, and that's false. Now, if we say that, okay, so putting answer 20 equal to C gets us a score of 18 because that's false. We can put answer 20 equal to A, and then we get 18 points another way. Remember question 20A said the maximum score is 18. Okay, so now I've got to make a little argument here, and that is okay. I don't think I have it on your handout, but or maybe I did. But anyway, there's a crucial point here that says every if 20E is true, so 20E is true, which says the only way to get a perfect score, the only way to get the maximum score is by getting question 20 wrong, then every valid graded list of score M is the maximum score, has X20 false. That says that if you achieve the maximum score, then you question 20 wrong. Okay, now, so we've got solutions 4 and 5. It says, okay, so now it's like M equals 18. But here's the problem. Then we look at that solution 6 on your list there. And here we get another way to score 18. And it says, and that would be a valid graded list of score 18 in which X20 is true. So we got so M cannot be 18. I showed a minute ago M can't be 19. Now it can't be 18. All right. Well, okay, 17. Well, it turned out it can't be 17 either. The same argument. Every valid we get examples where we get 17 and it's valid graded of score 17 and has X20 is true again. So I okay. So so is this the end of the story? And the answer is no, because all of this was predicated on the idea that 20D is false. Now look at 20D. 20D says that the maximum score that can be achieved on this test is indeterminate. Okay, so various people claimed on the as they were reporting on this, working on this problem, they said, well, that has to be false, because look, we've got only 10 to the 20th possibilities, and so it seems that it's very determinate. It's a large number, but anyway, we could determine what's the maximum score. On the other hand, that argument is fallacious. It's wrong, because the question 20 goes beyond what we're allowed in this thing, because these functions, these little f functions here, are not referring only to alpha and beta, but they're referring to capital F itself. So the question 20 asks a global question about the set of all solutions and all graded exams, And it's not just a statement about the grading of one particular exam. And so here we have the case where paradoxes can occur because we're not talking locally, but we're talking globally about this, about the quantified set of all ways to grade. So in the I don't have time to go through the details, but in your handout you can see there at the bottom it gives a couple of examples of small questionnaires that ask global questions. And the first one says, answer 1 is incorrect, answer 2 is incorrect, and problem says that some answers can't be graded consistently, and no answers achieve a perfect score. So these are examples of questionnaires that talk about global properties of the whole system, instead of just locally about one exam. And so you go into the logic of this, and it turns out it involves quantification over x's and over and over the answers, and you get formulas that this f expands into something that has capital F again on the right-hand side, and that would have to expand over and over again until we get to a fixed point or something. And sometimes it turns out that everything collapses and we can evaluate the right-hand side exactly without ambiguity, but sometimes we get into cases where we cannot. And so there are examples given there showing that it's not so easy as it seems. In fact, there's a one question exam with one letter answer, and it's given there in the second last paragraph. It says, question 1, A, the maximum score is 1. That's the whole exam. Now it turns out that the maximum score in that example is indeterminate. If the grader says that answer was correct, then let's see. So the maximum score is 1, and so if I agree that the maximum score is 1 is true, then the only possible score is 1. And if I conclude that, however, the maximum score is not 1, 0, then that's also consistent. So both of those arguments are logically consistent. Both of those grades are logically consistent, depending on how we interpret the statement, and therefore the maximum grade of that little exam is indeterminate. Either way we wanted to read it, we could say we could defend our answer as being consistent. So therefore, it's conceivable that the question, this modified questionnaire, problem 91, has a indeterminate answer, and therefore question 20 now, when you answer indeterminate for question 20, that might be true. It might be that is correct, that the maximum achievable on this test is indeterminate, and that is true. So that's what solution 7 shows. So if you look at solution 7 in your handout, there's a solution 7 here, and it ends with a capital D, which says that it's true that the maximum score is indeterminate. And in that case, it's kind of interesting because that answer number 7 has a score of 19. So here it's great because we have achieved a score now of 19, and that resurrects this one, which we had to throw out, because now this one is a valid thing because it's not possible to achieve 19 only by getting this one wrong. It's possible to achieve 19 without getting this one wrong. Therefore, both of these are valid gradings now, and therefore the score is 19. Okay, so here is the paradox then. If we decide that the maximum score is indeterminate, then we can determine definitely that it's 19. But if we decide that it's determinate, then we can't evaluate it. Here we are. And that is, I think, at least amusing. Okay. So it becomes also a research problem in the sense that anyone working on proof of correctness of programs, I think this is an interesting problem to prove correct, to prove the correctness of my back 20 program, and therefore validate all these things I'm saying about the paradox. Okay, that's it. Questions? Yeah, Barry? I mean, it is Barry or Brett, yeah?
So isn't what you've done here, so in question 90, in 90, so in this version over here.
The second version first?
Sorry, let's step back a second. So in one of these versions, you can, so in the original toy problem,
Yes.
you can express that entire thing in proposition logic.
Yes.
But in a sense, in the second problem, you require, come back to Steve's question, you do have a problem at this point which requires quantification, because your grader is acting as an adversary because he can decide,
Yes.
in a sense, how he's going to grade a particular question, and so therefore you don't have a single assignment to the formula anymore, but it's a function of how your grader responds. So
Yeah.
you've gone from
this grader had two ways to respond. Yeah.
Well, that's just because it's these are
Yeah.
alternative solutions
Yeah.
to the propositional
No.
formula, but in the second
Yeah.
version, you require
Yeah.
quantifications.
Yeah.
To a different,
Yeah.
it has become a game.
Well, even the first version had quantification hidden, though, because when I said that 19 was the maximum score, it still used the game idea. That is a global question. In both cases, it just turned out that by simple reasoning we could show that it was 19.
But I suppose the solution, the paradox is simply is a consequence of this particular problem has if you model this as a quantified Boolean formula.
Yeah.
So one of the decisions that the adversary gets to make is that this thing has a indeterminate answer. As a consequence, then there's only one strategy to solving the Boolean formula, and that is that n must be 19.
Yeah, right, and so those are both consistent in ways. Right. Okay. So I ran across this as I was trying to fix his original problem, and let's see. I wanted to let's see what else did I want to say in that regard. Oh yeah, it's a little bit like the paradox of the unexpected hanging. Do people know the unexpected hanging? Anybody? There's a man who's told that he's going to be hanged. He's in the death row and he's going to be hanged either on Monday, Tuesday, Wednesday, Thursday, or Friday. And he's also told that it's going to be a surprise. The day that he's hanged is going to be a surprise. So, so he says, well, that's interesting because it couldn't be Friday because if I haven't been hanged on Monday, Tuesday, Wednesday, Thursday, or Friday, I won't be surprised. So therefore, it can't be Friday. Okay. well, then it can't be Thursday because if 3 days go by and I know it's not Friday. It's so he's feeling pretty good. He can't be happening. So that's the paradox. And he was hanged on Thursday and he was surprised. Okay, so I've been asking you questions all day. Tomorrow night is your chance to ask me questions. I'm going to answer every question on any subject, and I'm going to go fast so that you can ask lots of questions. And that's tomorrow at 6 o'clock. Is that right? Somewhere in this building. So, okay. Thanks a lot.